Alright, let's start our review for Assessment 7. Determine the factors and the roots of the polynomial. So first we're going to factor it, and once we have the factors, we'll be able to figure out the roots. Now when I start working on factoring this, my first step always is to look for a GCF. Notice that this one's cubic, right? So I can't just dive right into a magic X. The magic X is only for quadratics. So I'm first looking for a GCF. 3, -11, and -20. They don't have any common factors, but each one of these terms has X. So I'm going to start by dividing each by X. And that'll be 3x squared minus 11x minus 20. At this point, I have a quadratic. Now is the time to set up the magic X. 3 times -20, factors of -60 that add up to -11 are -15 and 4. Leading coefficient is 3, so I'll divide by 3 and then simplify the fractions. Where's my simplified fractions? So my first factor will be x minus 5 and then 3x plus 4. Notice that I'm not going to drop the GCF. The GCF is one of the factors. So the factors are x minus 5, and 3x plus 4. If I want to find the roots, I have to set each factor equal to 0. The first one is easy. I don't really have much to do there. The first root is 0. The second root I'm going to get by solving x minus 5 equals 0. Add 5 to both sides. X is 5. That's my second root. Third root I'll get by solving x plus 4 equals 0. Subtract 4. 3x equals -4 divided by 3, -4/3. Okay. Find the inverse of f of x. To find any inverse, I'm going to follow the steps. Replace f of x with y, minus 3, and switch x and y. Those are the first two steps. Looks a little ugly up above. Okay, my next task is to isolate y, solve for y, or get the y by itself. So in order to do that, my first step will be to add 3 to both sides. These are not like terms, so I'm not going to try to combine them. Y plus 1. And to get the y by itself, right, to get rid of this cube root, I have to cube both sides. So this side becomes x plus 3 cubed. You don't need to multiply it all out. You don't have to do x plus 3 times x plus 3 times x plus 3. Just leave it in this form. Equals y plus 1. Subtract 1 from both sides, and we'll get x plus 3 cubed minus 1. That is my inverse. My last step is to write it. F inverse of x is x plus 3 cubed minus 1. Notice that the inverse of a cube root function is a cubic function. The inverse of a cube root is a cubic function. Okay, next up, solve this absolute value equation. We haven't done one of these for a while, but to solve an absolute value equation, it's a lot like solving a square root equation. We're going to start by isolating the absolute value. So I have to get this part by itself. I see a square root equation down below. I'll go ahead and highlight the square root part. I'm going to have to isolate that as well. So I have to isolate, I have to get that part by itself. So I'll do subtract 5 first. 2 absolute value of x minus 3 equals 8, and then divide by 2. Absolute value of x minus 3 equals 4. Now, once I have the absolute value isolated, then I'm going to write two equations. The first one's easy, just take the bars off. The second one, set it equal to -4. Change the sign here. Solve these by adding 3 to both sides. X could be 7, or x could be -1. So there are two solutions for most absolute value equations, 7, or in this case -1. And of course, if you want to check those, you can plug them in. Plug in each value. Here would be a check. 7 minus 3 plus 5 equals 13. Okay, so absolute value of 7 minus 3, so that's 4. Absolute value of 4 is 4. and this is 8 plus 5. Oh, that is 13. Okay, that one worked. And then I could try the -1 as well. -1 minus 3 plus 5. Okay, -1 minus 3 is -4. But -4, the absolute, so this one also works. This is a little hard to see. -1 minus 3, the absolute value of -1 minus 3 is 4. Okay. Here's a function, f of x is 2x squared minus 3x plus 5. My job is to find f of -3. There's a couple ways you could do that. If you're struggling with like what am I even supposed to do in this problem, notice that this says f of x, and the question is f of -3. The x has been replaced by -3, and that's exactly how I do the problem. I replace each x with -3. And I've got to follow my order of operations. I do exponents first, so -3 squared is +9. And then I do multiplication, -3 times -3, again, +9 there. 18 plus 9 is 27, plus 5 is 32. Okay, the other way to do this problem is using synthetic division, because synthetic division we can use in place of plugging numbers in. I'll put -3 in the box. Here are my coefficients, 2, -3, and 5. Bring down the 2, multiply, so that's -6. Add these, so that's -9. Multiply, I get 27. Add those, and I get 32. So however you choose to do it, you can plug the number in or you can use synthetic division. You get the same answer. The remainder is the number you would get by plugging it. Okay, next. All right, hopefully I'm going to remember to put that arrow on before I copy it for you. We are working on a square root graph. This is a transformation of the original graph, the square root of x. I know that shape is a square root graph, okay? Solution, or solutions of f of x. Well, a solution is just an x-intercept, so here's the solution right here. It's -2. There's only one. Boop. Interval of increase. To do intervals of increase, decrease, or domain and range, I'm going to be smart if I will label the points. So I'm going to label the left and right of the graph, the top and the bottom. This point right here is -3, -1. And this arrow, infinity, infinity. To get here, I have to go over and then up. So it's infinity, infinity. If you imagine that you're getting on a roller coaster right here, right at the beginning of the graph, and you're going to travel along that roller coaster, it's uphill the whole way. So this graph increases from -3 to infinity because I have to answer these interval questions. I frame the intervals of increase and decrease according to x coordinates. So -3 to infinity. Only the x's matter for intervals of increase and decrease. Now, if the whole graph is increasing, that means there is no decreasing part of the graph. The domain, to do the domain, my strategy is to cover up the graph and drag the paper from left to right. So I'm going to look to see what the x coordinate is at the first point. Right there it is, -3, and all the way to infinity. And actually, I want to include -3, so I'll use that. And then to do the range, very similar. I'll start at the bottom of the graph, -1, and I'll go to the top. I'm looking at the y values, infinity. And again, I want to include -1. Write the equation of the graph. Well, I know it's a transformation of the square root of x. I notice that the graph went to the left 3 and down 1. So I've got my square root of x. To make it go left 3, I need +3 and then down 1. Okay. Very similar to number 3, I have to start solving this by isolating the square root. So I need to start by subtracting 4 from both sides. I get the square root of 2x minus 1 equals 5. And to solve a square root, to kind of undo the square root, I have to square both sides. This side will be 25, and when you take a square root and you square it, you get the radicand, 2x minus 1. Now it's just a simple two-step equation. Add 1 to both sides. 2x is 26, divide by 2, x is 13. Okay. Now it says I need to check, so I'm going to come over here to check. I'm going to check by plugging in my answer into the original equation. So here's the, move that over a little bit. So I'm at 2x minus 1 plus 4 equals 9. Okay, where the x is, I'm going to put 13. Okay, and now I'm going to simplify. So 2 times 13 is 26, and 26 minus 1 is 25. So this is the square root of 25. And the square root of 25 is 5. And 5 plus 4 is 9. 9 equals 9. Notice that I didn't change anything on this side in my check. I'm only working down, not moving things left to right as I'm checking. Okay. Ooh. Solution in a solution set. There it is. Okay. Next, we're going to simplify these expressions. And the final answer should have only positive exponents. Now, there's multiple ways to do these. First, I could use the exponent rules. That's one way to do these. So I could use my distributive rule first to bring this 3 onto the 2. So it would be 2 cubed. And then the power rule. The power rule says if you raise a power to another power, you multiply. So that would be to the 12th power. And that's 8x to the 12th power. 2 cubed is 8. The other way to do this problem is using expansion. So when something is cubed, it means you have 3 of them. So I'm going to say, okay, my first one would be a 2xxxx, right? 2 times x times x times x times x. And then I've got another 2 times x times x times x. Then I got another 2 times x times x times x. This is the visual approach, the expansion approach. And then I'm just looking to see, okay, what's being multiplied here? Well, for the coefficient, it would be 2 times 2 times 2, that's 8. And for the variables, I've got 4x's, 8x's, 12x's all being multiplied together. So that's 8x to the 12th, whether I'm using expansion or the rules. Okay. Next one, I could use my exponent rules, my quotient rule, to simplify this. The quotient rule states that when you're dividing, you subtract the exponents. 4/6 is what 4/6 always has been. It's 2/3. I'm just simplifying a fraction, 2/3. X to the -5th. And then I'm like, okay, wait, negative exponents, I have to flip. So I'll finish this problem by flipping the x into the denominator like that. Okay. The other way that you can do this problem is using like an expansion method. So I can say, okay, 4x to the 5th, that's really 2 times 2 with 5 x's. And 6x to the 10th, that's 2 times 3 with 10 x's. 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then I look to cancel. I'm like, okay, I got a 2 in the numerator and 1 in the denominator. And I can cancel out 5 x's from the numerator and 5 x's from the denominator. And I am left with a 2 in the numerator, a 3 in the denominator, and then 5 x's in the denominator. So same solution, same answer, just 2 different methods. Okay, on the back, we are going to multiply and simplify. Now when you multiply, you're going to multiply coefficient times coefficient and radicand times radicand. So my coefficient here is a 1. 1 times 4 is 4. And then I'm going to multiply the radicands. 8 times 2 is 16. X squared times x is x cubed, y squared. Y times y is y squared. Now, you don't necessarily have to do the factor tree or birthday cake for 16 because you know the square root of 16 is 4. You can just bring out a 4. It's certainly not incorrect to do a birthday cake or a factor tree for 16. It's just 2 times 2 times 2 times 2. So that will also work if you want to just go ahead and simplify square root of 16 is 4. You can also do that. But I'm going to go ahead, because I've noticed most students like to expand, I'm going to do it that way. Okay, because it's a square root, I'm going to do groups of 2. I'm going to bring out a 2, bring out another 2, bring out an x and a y, and all that's left under the radical is x. This gets multiplied together. 4 times 2 is 8, times 2 is 16, x, y, square root of x. Same idea next. Coefficient times coefficient, radicand times radicand. 8y, cube root of 81, x to the 8th, add these exponents, 5 and 3 is 8, y cubed. Okay, for most students, the expansion method works well for these, so that's how I'm going to do this one. 81, if you want to make a factor tree or birthday cake for it, it's 3 times 3 times 3 times 3. I've got 8 x's, and I've got 3 y's. Because this is a cube root, I'm looking for my groups of 3. 3, 3, and 3. Okay, it's like, okay, what comes out, what stays under the radical? Well, I'm going to be bringing a 3 out. This is the first one. I'm going to be bringing out a 3, so this will become 24, 8 times 3, right? I'm going to bring out an x and another x, so that's x squared. And I'm going to bring out a y, so that's y squared. There's already one y out here. Bring another one out, it becomes y squared. What's left under the radical is 3x squared. Didn't quite have enough room for that, but that's okay. Okay. All right, next. Simplifying radicals where you're adding or subtracting. You cannot add or subtract unless the index number is the same and the radicands are the same. So when I'm looking at these and I see that the radicands are not the same, I know that I need to simplify them first. So I will do 12 is 223. Can't simplify this one. 20 is 225. And again, I'm kind of taking some shortcuts here. Take your time to make your own factor trees for 20 and 12 if needed. Here's 12. Okay. Circle groups of 2. So I'm going to bring out a 2. This becomes 6 square root 3 plus 4 square root 3. Bring out a 2 here. Minus 10 square root 5. Okay. Now I'm looking to see what I can combine now that I've simplified. These are my like terms. 6 square root 3 plus 4 square root 3 is 10 square root 3 minus 10 square root 5. As tempting as it is to put those together, you can't because the radicands are different. Okay, next problem is similar. Same idea. I cannot simplify these until I have simplified each radical. I can't add them together in their current, I guess, condition. So I'll make a factor tree for 27. I already know it's 3 times 3 times 3. I'll make a factor tree for 75. 25 times 3, 5. It's 553. And the square root of 16 is one that I already know. Square root of 16 is 4. I don't necessarily need a factor tree for that. Okay. Square roots, I'm bringing out pairs. So this becomes negative 9 square root 3. Bring out a pair. Minus 10 square root 3. Plus 8. Okay, here are my two like terms right here. Negative 9 square root 3 minus 10 square root 3. That's negative 19 square root 3 plus 8. Can't combine those. Solve and check. Another radical equation. I'm going to solve this by isolating the cube root first. This says 3 times the cube root of x minus 7. So I'll start this by dividing by 3. Oops, I don't need that. Cube root x minus 7. was doing so well with the pen until right now. Now I've made 2 mistakes. Very ugly. Okay, now to undo the cube root, I have to cube both sides. Cube root x minus 7 cubed. 4 cubed is 64. Cube root of x minus 7 cubed is x minus 7. Finish by adding 7 to both sides. And this will be 71 equals x. Okay, it says solve and check. So I'm going to come over here to check my work. I'll recopy the original equation. And then I will start by plugging in 71. Okay, 71 minus 7 is 64. Yeah, it actually is. Just checking that in my head. The cube root of 64, right? This is a group. Its cube root is a group. So first I have to figure out what 71 minus 7 is. Now I need to take the cube root of 64. It's 4. 12 equals 12. It works. So 71 is x. Okay. These next 3 are all new. Our newest topic, rational expressions. So our strategy, whether you're simplifying or multiplying or dividing, is to factor and cancel. So this numerator cannot be factored, so I'll start just by putting it in parentheses, put any linear factors in parentheses, but the denominator can be factored. It's a difference of squares. 2x plus 3, 2x minus 3. Now, if you would like to do that one with a magic x, of course you can. 4 times negative 9 is negative 36. No middle term, so put a 0. Factors of negative 36 that add up to 0 are 6 and negative 6. And then you divide by 4. And simplify. This tells you 2x plus 3. This tells you 2x minus 3. So those are my factors. Some of you guys are factoring those quickly. Some of you want to use a magic x. Doesn't matter. And then I look to cancel. I'm like, okay, here, I can cancel 2x minus 3's. Those are gone. What's left? Got a 2x plus 3, but it's in the denominator. I need a numerator, so 1. When you cancel 2x minus 3 over 2x minus 3, that's equal to 1. Okay, next. Factor and then cancel. Again, the numerator, x plus 4, x minus 4. And I can factor this denominator using a magic x. 24, 14. Factors of 24 that up to 14 are 12 and 2. Divide by 3. X plus 4, 3x plus 2. Okay, I look to cancel, and I can cancel these x plus 4's, and I end up with x minus 4 over 3x plus 2. And if you can keep them in parentheses or not. Doesn't really matter at that point. Okay, next we're multiplying. The strategy for multiplying, very similar to simplifying, is to factor and then cancel. So I'll rewrite this. I can't factor the numerator, so I'll put it in parentheses. That's a linear factor. I can factor the denominator. I'll use a magic x for that. Factors of negative 5 that add up to negative 4 are negative 5 and 1. Divide by 1. X minus 5, x plus 1. Oh. I've got to adjust mine so it matches your paper. Okay, now mine matches your paper. I'm going to factor x squared minus 1. That's x plus 1, x minus 1. And I'm going to factor this denominator. 3x plus 6 can also be factored. I know it's not quadratic. I'm not going to use a magic x for 3x minus 6, but it does have a GCF, which is 3. 3x minus 2. Oh, these are pluses. 3x plus 6. 3x plus 2, sorry. Okay, now I look to cancel. The fun part. X plus 2's gone. X plus 1, gone. What's left is x minus 1 over 3 times x minus 5. Simplify, assume no denominator equals 0. Now, this assumption that the denominator does not equal 0, we're going to get into that next week, what that means and why we have that as part of the directions. For now, just do what we've been doing, which is just factoring and canceling. We're lucky because these are already factored. So really, I'm just going to do my first step, which is to keep, change, flip. So let me keep this and change to multiplication and flip. Normally, the next step is to factor, but since it's already factored, all I need to do is cancel. So I'll cancel the x plus 5s, and I will also cancel x minus 4 with 4 minus x. Now, those are not identical factors, but we know that those are equivalent to -1. Ooh, I see something else. I can also cancel this too. Okay, so in my numerator, I have x times -1, that's negative x. And then at the denominator, I have 3 times x minus 3. Okay, another graph to finish. And let me add the arrow here. Okay. I think I'm going to come over and do the labeling first because I see my first questions are interval of increase and interval of decrease. It's very helpful to have the graph labeled to do that. So this is 0, 4. And, ooh, this is a tough one. Imagine if that graph continues down, right? It will be at infinity, negative infinity, right? This arrow is just going to keep on going down, 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 down. So it's actually infinity, negative infinity. I know it looks like it's in quadrant 1. Got to think about the end of the arrow. Okay, so my interval of increase. Imagine I'm going to get on board right here, and I'm going to be traveling on this roller coaster. This is a downhill only roller coaster. So there is no interval of increase, but there is an interval of decrease. It starts at 0. We always look at x and ends at infinity. That's my interval of decrease, 0 to infinity. For domain, I go left to right, looking at the x's, 0 to infinity. I want to include the 0 because there's a point right there. And for range, I'm going to go from the bottom to the top. So negative infinity to 4. Include the 4. Okay, the equation of the graph. Okay, here I notice several things about this graph. First, I notice that it's been flipped over. It's like upside down. And I also notice that it's been shifted up 4 units. So I'm transforming the original graph, the square root of x. I've got to flip it over. That's this. And then I have to move it up 4 units. So I need a plus 4 outside of the radical.